Be doing electronegativity, which is how much an electron wants to get. How much an atom wants to get electrons. So, we'll get started on that, I suppose. So, as you can see here, I found a periodic table with the ranges, and it's all sorted by color. So, let's start with these ones over here. So these ones don't want, helium too, but not nearly as much as the rest of them in column one. All the ones in blue and then some of the ones in green, they find it pretty easy to just give away electrons, especially the ones in blue, so they can reach a point of one of the noble gases or something rather than actually gaining them, because they usually only have the one valence electron, so they need to grab. It would take a lot more effort to grab a bunch of them than to just lose one. So they're more than happy to give them away, and they don't really want electrons too much. Then there are the green ones who want them just a slight bit more than the ones in blue do, depending on what number. Yeah, they don't really care all that much either, but they'll take them. Then there are the yellow ones, which want electrons quite badly. It's not like they'll do anything for them, but they tend to like having them a lot. And then there are the ones in peach, which absolutely love electrons and will hog them from all other atoms. So, in other words, let's look around here. So pretty much, let's see which atoms are the most electronegative and the ones that, or what I'm trying to, so fluorine is the most electronegative. It has 4.0 as for how much it wants electrons, which is quite a lot, I must say. And then, look at me. I gotta get rid of that. I don't see the noble gases here, but noble gases don't really like getting electrons either, because they already have all the electrons they could ever want, so why would they want to get involved? So, and then the least electronegative is probably going to be, hold on, let me see what element CS is. C. Caesium. So caesium is probably the least electronegative of them all, only being 0.7. So let's talk about bonds and things like that. So you've probably already heard about chlorine and sodium, but they're a pretty good example of this. So sodium, sodium here likes to give electrons, because it's going to take a lot to get its shell full, and it only has the one valence one, so giving one away would do it better. But then there's chlorine, who is really close. It has 7 valence electrons. It just needs one more. So chlorine really wants electrons, and pretty much when the two manage to find each other, like in table salt. Okay, yeah, I know this is kind of bad, but roll with it here. So, the electrons that are shared between these two, they're not even sharing. So pretty much, chlorine just literally snatches because sodium is so, I mean, chlorine is so electronegative, and sodium is not so electronegative at all. So it's just going to steal the electrons rather than share it with them in a covalent bond, which we'll talk about in a second. But pretty much it just snatches the electrons away from it. So, like, I mean, it'll still have some electrons because, I mean, so it takes its electrons. So now this one's going to become a cation, which I just touched on in the previous video, and this one's going to become an anion because it just gained one. So that's what happens with. But then there are other examples where they actually share them, and this is quite important to life itself because H2O actually is a covalent bond. H2O is water, by the way. Just thought I'd bring it up. So let's draw that out. So water is just an oxygen with two hydrogens. So I'm just gonna make them a different shape because I can. Well, no, actually, no. That keep it consistent, okay? Just make them smaller. Yeah, but not too small. All right. This is pretty close. So no. All right. Yeah, I can. I don't think I can fit them in there as well as I hoped. So, and I don't know how to get rid of the text boxes right now without erasing them and ruining everything. So we're just gonna leave it as is. And then here, I guess, let me try clicking a little lower. We're going to add oxygen. So in a covalent bond, so oxygen has 6 valence electrons, while hydrogen it's one and only. It has its valence electron. It's one and only electron. Hydrogen wants to get to a state like helium because, unlike most noble gases, helium just needs 2 and it's fine. So hydrogen wants to be just like helium. So it's going to want to share with oxygen. It's going to share its electron with oxygen. While oxygen is going to share its electrons with helium. So oxygen, wait, let me see which one it's closest to. I forget. I know this is kind of unprofessional, so, but I don't have it memorized, so. Together. Anyway. So, yeah, I'm pretty sure it wants to be like, hold on, I don't know these ones' names. Oxygen wants to get to 8 as well, so oxygen likes getting 8 electrons. I don't know which atom exactly wants to be like, once again, and I'm not going to spend the whole video searching for it. So, yeah. And what happens is they get different polarities, which is what we were going to be talking about. So the polarity sign looks a little bit like an S, but then it looks like this, something like this. It's the delta sign, but in Greek, but it also stands for polarity. So, I mean, they're not going to be full-on anions or cations, though. They're just going to have a certain polarity. So oxygen, it loves to hog electrons. It just loves them a lot. It's very electronegative, while hydrogen is not so much. So it's going to have a partial negative charge, while hydrogens are going to have a partial positive charge because the oxygen is going to keep. I mean, it's still going to share them, but it's not going to spend as much time with the hydrogen as it is with the oxygen because the oxygen likes to have it around itself more than the hydrogen. And what happens is each side has has a different polarity. So this tends to happen with covalent bonds if they're not exactly the same, but they're not stealing it either. They're just kind of, sharing. But I mean, if they're the same, then it'll just stay like right in the middle of the two since both of them are sharing them. So there we go. Electronegativity. Thank you for watching. Bye.